Hi everyone, today I'm here to introduce our work, Optimum Pose and Shape Estimation for Category Level 3D Object Perception. My name is Jingnan, and this work is jointly done with Heng and Luca Carlone from MIT Spark Lab. For this work, we studied the problem of estimating the pose and shape of objects for category level perception. Let me unpack the title here. First of all, we want to tackle a category level perception problem where we are given 3D sensor data picturing an object, and we want to localize the object despite intra-class variability. And since we don't know the exact shape of the object we want to localize, our second goal is therefore to simultaneously estimate the shape as well as the 6-degree of freedom pose of the object while being robust to outliers. For example, we might be tasked with estimating the pose and shape of a car without knowing the exact make and model of the car, despite the fact that different car models might have very different shapes. Researchers have long been interested in problems related to category level perception. One category of approaches towards this problem consists of multiple stage methods. They first recover the positions of semantic keypoints in the images with neural networks, and then recover the 3D poses of the object by solving a geometric optimization problem. The optimization problem can nevertheless be difficult to solve, and many approaches are sensitive to outliers. There has also been a lot of interest in developing end-to-end methods that regress the object shape and pose from 2D images directly. Many of such methods use encoder-decoder architecture and may include an alignment loss to directly regress poses. However, they usually require extensive and difficult labeling. Our work in this paper falls into the multi-stage category, which we believe can utilize the advantages of learning-based and optimization-based methods. We developed the first certifiably optimum solutions to shape and pose estimation while being robust up to 90% outliers. To understand our methods, let's first take a look at our problem formulation, which is based on an active shape model. We assume we are given a list of CAD models for the object category we want to estimate, such as a list of CAD models for cars. We then detect semantic keypoints of such objects, and then express the shape of the object we want to localize, and hence the semantic keypoints as a linear combination of the given CAD models. Here is a video visualizing our active shape model and the effect of taking linear combinations of the shapes in our library of CAD models. The linear combination can produce any single car in the library, but also allows interpolating between multiple cars, making the model quite expressive in practice. In this example, by changing the parameters, we can interpolate from an Audi Q7 to a Hyundai. In practice, we can apply this method using a library including hundreds of CAD models. While expressive, the problem of estimating the pose and shape using an active shape model leads to a difficult optimization problem. Given the keypoint detection y, we need to solve the nonlinear cost function shown on the left. Our first contribution is that we developed the first certifiably optimum solver named PayStar for 3D category level perception. We decouple the rotation estimation from the translation and shape parameters. The translation t and shape parameter c can be solved in closed form, while the rotation r can be computed by a tight SDP relaxation. With PayStar, the solution can be still affected by outliers. To combat this, we equip PayStar with two outlier rejection schemes. First, we take sensor data as input, as well as outputs from neural networks for 2D semantic keypoints, and pass them to graph-theoretic outlier rejection layer to reject gross outliers. The rejection layer works based on filtering out geometrically incompatible keypoints, and is based on robbing, our previous work. To further increase robustness, we apply a graduated non-convexity scheme to the solver based on earlier works from our lab. We call the resulting approach PACE-sharp. Here are the results on the Pascal 3D Plus dataset. We tested our solvers on the car category, which consists of 10 CAD models of different cars. PACE-sharp achieves the best results among the methods tested. It achieves robustness up to 70% outliers, significantly outperforms other methods compared. Here are the results of running PACE-sharp on the ApolloScape dataset, which is a large-scale self-driving dataset collected in different cities in China. For this task, we use a test bed provided by the authors, which consists of a set of video frames without temporal information. We again achieved excellent results outperforming other methods on most testing criteria. Note that if provided with better depth and better keypoint detection, PACE-sharp can further improve its accuracy. In addition, our current implementation has sub-second runtime, with further room for speed improvements. Thank you for your attention, and please refer to the paper for more details.